Right, the simulation has finished running, and then we have a bunch of plots to analyze, and all the simulation results are saved in the designated folder location. So just to show you where they're saved, we can go back to the example folder here, and then since we ran case study 1.0, and you see the simulation outputs folder, so you can click there, and then you'll be able to see the PDF of all these figures that I'm about to explain, and then you'll see the raw data here. And let's actually try to talk about these plots. So the first plot is the pressure swing, the pressure profile for the assertion column number 1, which is basically this dark solid line, and then the gray one is column number 2. Notice that all the times one of those two assertion columns are always in the production phase or high pressure feed, right? This allows us to continuously produce purified oxygen. That's why we're running these two columns side by side. So the one is production phase, the other one is regeneration phase, right? So for the first assertion column, when it's repressurizing and a high pressure feed, the second assertion column is depressurizing and then doing low pressure purge. And then the second column is now repressurizing and then doing high pressure feed. The first column is depressurizing and doing low pressure purge. And you can kind of see these cycles, cycling back and forth, right? So that's the first figure. Second figure is the pressure profile inside the raffinate product tank. So you start out as some product raffinate product pressure, but then you go down because you're using some of the raffinate product to do things, right? You repressurize one of those assertion columns at a given time, and you might be also purging. So you lose some product, but then you end up generating them, and then once you reach the desired pressure, all the surplus are collected. They're actually basically uh, diverted to the raffinate feed reservoir from the raffinate buffer tank, right? So you actually, whenever there's this flat region, that's where we're doing net generation of the raffinate product, which is pure oxygen, nearly pure oxygen. So you can kind of see the raffinate tank pressure swinging as well. And then this is extract tank pressure. It's doing nothing. Isothermal simulation, and we're not interacting with extract tank anymore at all. So that's why the pressure is just constant. And then we can actually start to compare these figures for this is gas phase concentration. So figure 4 and figure 5. You can kind of compare them side by side. So assertion column number 1 to the left hand side and assertion column to the right. Two on the right. And you can kind of see this is the snapshot in time, right? So this is right at the end of the high pressure feed, which you're seeing that the nitrogen concentration, which is this darker line, actually starts to increase to a certain extent, right? The more the this mass transfer zone gets closer to the end of the assertion column, the nitrogen concentration would go up, and then the oxygen concentration would go down. So this is showing that the majority of the bed has been saturated with the feed, and it's showing an excellent bed utilization, right? So we're utilizing the bulk of the adsorbent inside this assertion column, and it's really important to actually have this mass transfer zone to be as thin as possible, because the more mass transfer resistance we have, the wider this zone would be, and then the little bed utilization would be lower because it takes more time for these bed adsorbents to be saturated with the feed. So these are gas phase concentrations, and then we can also see the corresponding adsorb phase concentration in the column 1 and column 2 to the left and to the right. So you can kind of see those information. And then here's basically real time the purity of the product in the raffinate tank on the left, and then the extract tank on the right. Again, extract tank, it's doing nothing there. We're not interacting with it, but raffinate tank, you can kind of see that the product purity, it's kind of decreasing, but it's really slightly so. but basically it's the mole fraction of light key inside the raffinate product tank. It's pretty pure. And we have bunch of performance metrics. So first one is purity. So as you can see, the purity in each product, each cycle, uh, purity inside the raffinate product tank in each cycle is plotted, and they're above 99.7%, which is pretty pure. And we also see some product recovery. So it's basically the amount of the desired product, in this case oxygen, collected divided by the total amount of oxygen fed into the uh, assertion column, right? So you see that at the fourth cycle, at the end of fourth cycle, purity is about 10.2%. This seems pretty low. However, that's not a concern, economic concern at least, and environmental concern, because air is everywhere. And typically, this air separation recovery tends to be really low. But this is a niche application where lower purity is acceptable, and this is actually pretty consistent with the paper that we got these simulation parameters from, Knaebel and Kayser's paper on July 5A oxygen simulation. And their work, they also basically attained about 10% of recovery. The other product performance metrics is productivity. So it's the amount of product generated normalized by the amount of adsorbent and time, right? So basically it's just telling us how fast are we generating this product. And in this case, it turned out that the productivity of the cycle at the end of fourth cycle is about 0.07 millimoles per kilogram per second. And this is energy required, so we actually need to compress the you know feed if it's not already at the high pressure, and sometimes pour vacuum down to the subambient pressure, which this was the case. So by taking account for those compression, the work done by the compressor and the vacuum pump, we're able to calculate the energy per required for generating one more of the product. And finally, we have the convergence plot, which is rather important. Cyclic steady state is the convergence criteria for PSA cycles. You can think of it as just because it's a cycle, we always go back to the starting point, and cyclic steady state is just asking ourselves how close are we relative to where we started the first PSA cycle. So R2 norm of the difference squared of these initial condition at each cycle is what we're using, and convergence criteria is 10 to the minus 8, and we're below that at the fourth PSA cycle simulation. So yeah, that's pretty much it for analyzing these results. And some nice comments: when we can interact with MATLAB with this command window. So if you type close or, it's going to close all the open figures, and then if you do clear or, suppose if you had any workspace variables, then we can erase them by typing in clear or, and then CLC just clears up all these comments. Thank you.